Building Information Modeling, BIM, is a collaborative working methodology for the creation and management of a construction project. This new working method integrates all the agents involved in the building process: architects, engineers, builders, developers, facilities managers, etc., and establishes a communication flow between them, generating a virtual model that contains all the information related to the building throughout its life cycle, from its initial conception, during its construction and throughout its useful life, until its demolition. Each agent involved in the building process is part of the BIM working method. Each of them has their own competences and access to the relevant part of the information. That is why it is essential that all of them know the BIM method and how its tools work. BIM is the evolution of traditional plan-based design systems, as it incorporates geometric, 3D, time, 4D, cost, 5D, environmental, 6D, maintenance, 7D, health and safety, 8D, etc. The use of BIM goes beyond the design phases, encompassing the execution of the project and extending throughout the life cycle of the building, enabling the management of the building and reducing the economic and environmental costs of operation. BIM platforms automatically update the information that is edited in any part of the model. This means that if an element is modified in a floor plan, it is automatically modified in the sections, elevations and 3D views, just as if a feature is modified in a listing, it automatically changes throughout the project. There is no possibility of human error. The information is always consistent. As all the agents work on a single model, there is no possibility of loss of information due to lack of coordination between versions handled by different professionals. By establishing this method of working in parallel, all the agents can propose from the beginning the options they consider most convenient for the project, directly involving the whole organization. The project is developed in real time in a coordinated manner in a collaborative environment, always under the supervision of the client. BIM allows any required information to be always available, both design and technical, costs, execution deadlines, maintenance, etc. It also allows modifications to be made in real time that will automatically update all these parameters, increasing the degree of personalization and adaptation of the project to the client's needs. Facility management tasks become much more efficient, as all the real information on the asset is available on demand. Environmental problems arising from the construction sector require tools to evaluate proposals that help to curb the consumption of resources and environmental impact. Life cycle assessment, LCA, is recognized as one of the most valid methods for the environmental analysis of buildings, although its application is complex and its standardization and simplification is necessary to make it operational, also in the design phase. The integration of LCA into BIM platforms simplifies the environmental impact assessment process. Currently, there is a scarcity of literature and development of simulation tools based on BIM models and linked to LCA for obtaining environmental impact results. It is therefore necessary to standardize LCA implemented in BIM platforms in order to simplify the process and obtain environmental impact results in real time from the design phase. Today, the LCA of the building is unfortunately not a factor of choice, but rather an outcome. It is still difficult for the actors involved in a building project to rely on LCA in their choices. However, developers of BIM software and solutions will play an important role in integrating LCA into digital models. From a building modeled in BIM, it is possible to calculate the LCA potentially without even changing the software environment. Therefore, LCA in BIM should be more automatic, more systematic and easier to achieve, allowing multidisciplinary teams in architectural projects to establish different scenarios from the point of view of the environmental impact of the building. Expectations and understanding of what BIM is vary greatly. While there is obviously a common consensus for those immersed in the BIM methodology, most of the construction industry is still struggling to understand what they will produce, issue and receive when working with BIM. In the example of an air conditioning system, an engineer might be expecting to receive dimensionally accurate duct layouts to ensure structural openings are properly sized. An architect may only need a zoning approximation to improve their circulation and space designs, while the reality is that the installer is only working on 2D schematics that are alien to the expectations of others. This lack of communication and common perspective leads to delays, friction and in many cases errors. Therefore, it is of crucial importance to properly define the degree of development, both graphically and in terms of the amount of information contained, of models and the BIM objects that make up the model in a project. BIM objects are geometric models made with parametric software in a way that allows their attributes to be modified. When we talk about BIM objects, we always refer to open formats. However, in the case of the term families, we refer to BIM objects that we create with a specific tool, Autodesk Revit. We can find different types of standards depending on whether they are family standards or BIM object standards. Family standards are intended to establish a creation protocol so that people know how to create new BIM objects for a given software, Revit in this case. Program configurations and modeling recommendations, such as the Revit style guide developed by BIM object. In contrast, BIM object standards advocate open formats and focus on the information they should contain in order to be usable throughout their life cycle. Examples are the NBS BIM object standard developed by the National BIM Society, UK, OBOS, Open BIM Object Standard developed by NatSpec, AU, and MasterPec, NZ, as well as the ECOB, BIM Object Creation Standard, NZ, and the ECOB, Open BIM Object Standard, UK. Regarding ECOB, produced by the ITEC, Institute of Construction Technology, it is based on the IFC scheme, extending it with a certain number of additional attributes and information. It is a standard that can be used both internationally and locally because it is adapted to the Technical Building Code, CTE, the Catalog of Construction Elements, CEC, and the regulations applicable to construction products. The key to a standard is to be able to synchronize data in an easy way and that the structure of the information coincides at the same time as the terms of the same. The GDO BIM standard has as its aim the idea of guaranteeing the traceability of information throughout the development of a project, for which it has sought to facilitate understanding and workflows between construction agents working in BIM. We can see that, in this process, the manufacturer plays a fundamental role in achieving this goal. BIM CIC Construction Industry Council Protocol. A supplementary legal agreement that is designed to be used by the parties involved in a construction project. It incorporates professional services engagements and construction contracts, a modification of the standard terms, creating additional rights and obligations for the builder and the contracted party to facilitate collaborative working, while safeguarding intellectual property and differentiating responsibilities between those involved. Regarding the stage of development of these BIM objects, the BIM CIC protocols in the UK detail a model production and delivery table, more commonly known as a responsibility matrix, to clarify what information will be produced at any given stage and by whom. In short, it assigns a load, level of detail, code to each building component or system at each progressive stage of the project so that the whole team knows what to expect. The basic codes differ between the US and UK conventions, which only serves to confuse the issue further. For this reason, it is vitally important to differentiate properly between the following concepts. These concepts often lead to confusion. The terms LOI and load come from British standard definitions and forced to the definition of BIM objects, where LOMD is the combination of both applied to the model scale, i.e. the project to be executed, while load comes from the American standard. In this course we differentiate load, level of detail, and load, level of development, by means of a lowercase o in the case of the former, but in reality, both acronyms are professionally used with the same acronym, LOD, although they are different standards, hence their confusion, among other characteristics that differentiate them. The use of BIM goes beyond the design phases, encompassing the execution of the project and extending throughout the life cycle of the building, enabling the management of the building and reducing the economic and environmental costs of operation. The BIM dimensions consist of sectorizing each descriptive phase of the building's life cycle, being integrated in a virtual graphic model considered as dynamic, since all this information can be changed according to the current state of the construction, design, execution, use and end of its useful life. The building reality is always supported by a virtual graphic model that adapts to it. Consequently, a very important fact to bear in mind is that during the entire life cycle of the project, from the idea to its demolition/deconstruction, and recycling, there is a continuous process of feedback. In other words, the BIM model is continually being modified, evolving, so that at any given moment reality and model are identical. BIM dimensions. 1D equals the idea. We start from an idea, a house for example, and define the initial conditions, the location, we make some initial estimates, surface area, volumetry and costs, we establish the execution plan, etc. 2D equals the sketch. We prepare the software for modeling, we project the first lines, etc. 3D equals information model of the building. From all the information gathered, we generate the 3D model that will serve as the basis for the rest of the project's lifecycle. It is more than a graphic representation of the idea. The 3D model is not only visual but incorporates all the information that will be needed for the following BIM phases dimensions. 4D equals time. To what could so far be considered static, the dimension of time is added. So, we can define the phases of the project, establish its time planning, as well as simulate time parameters, life cycle, sun, wind, energy, etc. And we can also simulate the time parameters, life cycle, sun, wind, energy, etc. 5D equals cost. This is the cost control and cost estimation of the project. The main objective of this dimension is to improve the profitability of the project. 6D equals sustainability or simulation. Sometimes called green BIM or green BIM, it consists of simulating the possible alternatives of the project to finally arrive at the optimal alternative. And all this before laying the first brick. 7D equals operation and maintenance or instruction manual. This could be said to be the manual to be followed during the life of the project, once built, for the use and maintenance of the project inspections, repairs, maintenance, etc. 8D equals health and safety. The use of BIM and Lean together not only produces an increase in the productivity of construction projects, but also means an improvement in the quality of the preventive measures that can be adopted in the construction phase. All this results in an increase in the quality of health and safety at work, better controlling risks and creating a better workplace for workers. Levels of development, LOD. The LOD is level of development defines the level of development or information maturity that an element of the model possesses, and this is the part of a component, construction system or building assembly. It should be clarified that the LOD does not refer to the entire project and is not linked to the development or construction phase. It is a classification scale of the level of detail that BIM objects will have according to the moment of development of the project. According to the international standards of the AIA, American Institute of Architects, the LOD levels range from LOD 100 to LOD 500. A LOD 100 would correspond to the most initial design moment, a LOD 300 would be a level of graphic detail corresponding to that of an execution project, and a LOD 500 would correspond to an as-built, which would be used for the management of the building already in use. However, as we will see below, the British have their own standards, defined as levels of detail, rather than levels of development, which, being more focused on graphical aspects, range from LOD 1 to 7 and are called LOD 1 brief, concise, LOD 2 concept, LOD 3 design development, LOD 4 production, LOD 5 installation, describes the construction, LOD 6 is built, and LOD 7 asset information model, asset information. Levels of information and levels of detail. This is the amount of non-modeled information that a BIM object has. For example, a family has its types, and within these types it can have a huge number of parameters that can range from something as simple as height and width to as complex as a mathematical formula that changes the spacing of the elements depending on the occupancy of the room they are in. LOI can be tables, specifications and parametric information. The term LOD, level of development, is sometimes misinterpreted as level of detail, LOD. The level of detail, LOD, essentially refers to the amount of graphical detail included in the model element. However, the LOD is a measure of the amount of information and the quality of the information. Roughly speaking, we could say that the LOD for the American standard is the sum of LOI and LOD of the British standard. The levels of detail are determined by letters A, B, C, or letters and numbers G0, G1, G2, depending on the country of origin and the definition to be considered. The English Standards and Publications PA 1192-2/3/4 and BS 8541-2011 define these levels. A.78 schematic, conceptual and defined. G0 symbolic. No scale, simply a suggestion of where the object will exist. For example, in the case of doors, this could simply be a black rectangle on a 2D wall. G1 placeholder. Although it may be to scale, the object may not represent the appearance of the final component. For example, in the case of doors, this would be a simple, plain object without frames, vision panels or hardware. G2 suitable for construction. This is where the representative geometry of the final component would be provided. It may not yet include hardware, as this would normally be specified separately, but could be an object downloaded by manufacturers. G3 High Resolution, fully detailed object. Normally only used for visualization or, indeed, for manufacturing. Level of model definition. Sometimes the term load, level of detail, is used to refer to the model, and not to the elements that make it up. But this leads to confusion, and other authors use the term load when referring to the model, the project to be executed, instead of the elements that make it up, the BIM objects that make up the project graphically. The definition level corresponds to the linear evolution of quantity and richness of information of a construction process. It always increases over time and refers to the project model, costs/budgets and time planning. Load 100, pre-design stage. Contains basic element information such as area, height, volume, location and orientation. This information should be considered as approximate. The element may be represented graphically in the model with a symbol or other generic representation. For example, in the case of a partition wall, we would have the dimensions of the partition wall. Load 200, schematic design. General model in which elements are modeled with approximate quantities, size, shape, location and orientation. We can also attach non-geometric information to the elements of the model. Load 300, detailed design. Precise and geometrically defined modeling in detail, as well as its position, belonging to a specific construction system, use and assembly in terms of quantities, dimensions, shape, location and orientation. Non-graphical information may also be included to the element. Load 400, manufacture and assembly. The object is defined in detail geometrically, as well as its position, belonging to a specific construction system, use and assembly in terms of quantities, dimensions, shape, location and orientation. It includes specific information for design, commissioning/assembly and installation. Non-graphical information may also be included for the element. Load 500. Elements are modeled as assemblies built for maintenance and operations. In addition to the actual and accurate information on size, shape, location, quantity and orientation, non-geometric information is attached to the modeled elements. Load 000. It includes the characteristics of the land, position, height, topography, geotechnical, state, etc., those of the surroundings, climate, connections, sunlight, distances to reference points, local needs, etc., and those of the plot, cadastral reference, surface area, divisions, owners, endowments, etc. The target element is not geometrically defined, but its basic dimensions, position, location and orientation with respect to the whole site and its surroundings are defined. It is mainly based on non-graphical information linked to the element. Load XOO. Included in this level of development is an activity that has already begun, such as the 3D scanning of existing buildings that are to be permanently demolished, or moved from their original site, remaining with the corresponding development permanently or temporarily in a virtual world with a specific degree of definition and likely to be the subject of further reproduction or development. The object element will be fully geometrically defined and will add new concepts such as distance from which it is visible and different degrees of geometric definition according to distances. For example, the texture shall be derived from the characteristics of its surface materials. It is possible to add other non-graphical information linked to the element. The environmental impact categories represent the environmental impacts of interest to which the Life Cycle Impact Assessment (LCIA) results will be assigned. In other words, they are the environmental impacts for which results are desired. There are a multitude of environmental impact categories, and the selection of one or the other will depend on the objective of the study, the target audience, and the level of accuracy of the results required. In some cases, a substance contributes to several impact categories and should therefore be considered in all impact categories. Functional unit, quantified performance of a product system for use as a unit of reference, definition according to N ISO 14040-2006. The functional unit defines how the identified functions or performance characteristics of the product are quantified. The main purpose of the functional unit is to obtain a reference that allows the standardization of LCA results related to material flows, input and output data, of the construction product and any other information, in order to produce data expressed on a common basis. UN N 15804, Article 6.3.1. In principle, the comparison of products based on their EPBD is defined by the contribution they make to the environmental performance of the building. Therefore, the comparison of the environmental performance of construction products using EPBD information should be based on the use of the product and its impacts on the building and should consider the whole life cycle. All information modules, UN N 15804, Article 5.3. Information module, data collection used as the basis for the Type 3 environmental declaration, covering a unitary process or a combination of unitary processes that are part of the life cycle of a product. Declared unit, quantity of a construction product to be used as a reference unit in a EPD for an environmental declaration based on one or more reporting modules, definition according to UN N 15804. The declared unit is used instead of the functional unit when the exact function of the product or the scenarios at building level are not established or unknown. The declared unit is to be applied when a EPD covers one or more life cycle stages by means of information modules, i.e. in the case of a cradle-to-door EPD and a cradle-to-door with options EPD, and when the EPD is not based on a full cradle-to-grave LCA. It provides the reference allowing to combine the material flows attributed to the construction product and to combine the environmental impacts for selected stages of an incomplete life cycle of the construction product, referring to typical product applications. The environmental impact indicators covered are as follows. BIM object platforms. Nowadays it is possible to find several websites where you can download free resources for BIM software, libraries of BIM objects of different load levels, families or components, materials, plugins, manuals, etc. Remember that BIM objects are geometric models made with parametric software in a way that allows their attributes to be modified. When we talk about BIM objects, we always refer to open formats. When we talk about families, we refer to BIM objects that we create with a specific tool, Autodesk Revit. BIM tool is an intelligent BIM platform for the industry. It has a complete catalog of products in BIM standard, allowing buyers to download and work with them on their projects, where it brings together the entire AEC construction community, material suppliers and manufacturers, architectural, design, engineering and construction professionals. BIM and CO is very present in the world of construction digitalization, offering all the agents involved in construction and manufacturers solutions to manage and share their BIM objects. BIM Object is one of the most powerful websites for free downloads of BIM objects. Once registered, it is possible to download all available objects for Revit, BIM components for ArchiCAD, Allplan, Rhinoceros, SketchUp, etc. It is also possible to install its plugin for various BIM software and have access to its catalog from the software. Synchronia.com is a totally free professional services web platform, offering BIM models, catalogs, technical information and product presentations, and consultancy for technical offices of companies. Synchronia is also a space to find new clients, interact with other professionals and manufacturers, or publish new projects. Synchronia selects brands of excellence for different product categories, with the possibility of downloading BIM models developed by manufacturers in collaboration with Autodesk, its technological partner, completely free of charge. That is why the BIM models are mainly developed for Autodesk Revit. Bimatica is a social platform that offers specialized knowledge and information on technologies, methodologies and products related to the construction sector and especially BIM. It is not only possible to download BIM objects, Revit, ArchiCAD, IFC, EcoSim, etc. families, as well as other files in 3D blocks, datasheets, etc. but also to order them if they are not in the BIM library. Completely free of charge. ArcAT, in essence, it is a BIM library. In addition to BIM objects, it is possible to download technical specifications of construction products. They even have their own mobile app. BIM components are Revit objects and families as well as DWG files. BIM Community, its aim is to be the international reference portal in Spanish in the BIM world. The main resource that can be found on this website is information in the BIM environment, software, mobile applications, guides, BIM servers, books, BIM components, etc. and of course, links to the main websites that offer all these resources. bimstore.com.uk is basically a BIM library for Revit, as well as a BIM object factory. As a curiosity, BIM Story, its augmented reality viewer, allows you to see manufacturers' BIM components in 3D. Regarding the above-mentioned platforms, many of them consider facilitating the load level of the uploaded BIM objects for the users. There are also several such platforms that already take environmental data into account in the development of BIM objects. Uses of Load 600 analysis. The element should include its dismantling, demolition and recycling details. Composed mainly of non-graphical information. Cost. Estimation of costs/expenses according to the recycling needs of the element, linked to issues such as useful life, depreciation, renewal value, etc. specific to the site and the distance to other environments, recycling points, factories, urban centers, protected areas, etc. Programming. The item shall consider its useful life, reliability in use and costs arising from recycling, as well as related fees or penalties. Coordination. The element can be used to coordinate with other elements of the project based on recycling schedules, as well as its effect on the other elements of the project during its modification, removal, decrease in efficiency, toxicity, etc. Consequently, under the same criteria and based on current standards, it is possible to insert environmental impact data into BIM objects, as will be developed in the following modules of this course.